Hi everyone, my name is Yiklun, and in this presentation, I'm going to talk about change point detection in dynamic graphs with a generative model. And for the outline, I will first talk about the type of data that we're working on. And you might be wondering, how does a generative model can be helpful in change point detection? So I would like to first talk about a model specification, and then from there I would like to draw the connection to change point and the associated detection problem. And then I will talk about the learning methods, which involving two components. One is ADMM and the other one is launch-driven dynamics. And lastly, I will use real data experiment to demonstrate that a generative model can be helpful in change point detection. So the type of data that we're working on are graphs, and graphs are often used to describe relational phenomena in many domains. And relational phenomena can also progress in time. So here we're looking at the correlation network of 29 stocks in the Dow Jones Industry Average on 3 particular dates. So as you can see that for real data, as the time progresses, the structures can be very different over time. So it is practical for researchers to locate the time point where the structures have substantially changed for their research. There is some existing work on change point detection for graphs. So for example, K et al. Proposed to detect the structural change using separable temporal exponential random graph model. They relied on user-specified network statistics, but the choices that are useful for the detection are often not known to the modeler. There are many latent-based models proposed for change detection. They focus on node-level representation, which may not be powerful enough to capture the information of the entire graphs. So in our work, we focus on the following aspect. So instead of specifying the network statistics, we want to learn the pattern from data to determine the structural change. And we also focus on graph level representation. And lastly, we want to explore how generative model can assist in change point detection task. So first, let's introduce some notation for network. So for a node set from 1 to n, let's denote YT, a binary n by n adjacency matrix, as a network at a time point t. The diet YTIJ in 0 or 1 indicates the absence or presence of an edge between node I and node j at time t. So here we are looking at a graph and also the associated adjacency matrix for the same graph. So here, the rows and the columns are corresponding to the nodes, and then the entries in red are indicating that there's an edge between two particular nodes. And here, the observed data are Y1 to YT, a time sequence of a network. So for a network YT, we assume that there's a latent variable ZT that is in RD such that the network YT can be generated from the following decoder. So we write it as a YT following a distribution P of YT given ZT. And we also impose that when given ZT, the distribution for the graphs are dyadic independent. And we also impose a learnable prior to the latent variable. So we write it as a ZT following a marginal P of ZT. And we let this marginal distribution be a normal distribution with mean vector mu t and identity covariance matrix. So now let's look into the graph decoder. So the graph decoder, which is a dyadic Bernoulli distribution with a Bernoulli parameter for dij, denoted as Rij. So this is the parameter for the YTIJ equal to 1 given ZT, and we let this parameter be a neural network. So the function h is parameterized by a neural network, which input the latent variable ZT and output a real value n by n matrix. and followed by a element-wise sigmoid function to convert the real value n by n matrix into a probability n by n matrix. So now let's further look into the neural network, which is the function h. So essentially we use a multi-layer perceptrons, transferring the latent variable zt that is in Rd to two particular matrix. So one is ut that is in R n by k, and also vt in n by k. So the output for the neural network is that for directed network, the output is uv transpose. So we'll get a n by n real value matrix. And for undirected network, we have a uu transpose. So we let the latent dimension d and k be smaller than the number of node n. Just to give you a sense for the dimension, for the simulation study in this work, we use for node set of 100, we use the latent dimension d be 10 and also the latent dimension k be 5. And the parameter for the neural network in this work is denoted by phi. So we write it as yt following p of phi of yt given zt. So here is an overview for our proposed framework. So we observe a sequence of network from y1 to yt, and then we assume that for each of the network, there's a latent variable zt such that the network yt can be generated from the latent variable with the following graph decoder. And then we also impose a learnable prior for the latent variables. So it is worth pointing out that the simplicity for our framework, we don't need any encoders. We just need a decoders in our framework. And we also call the zt as a graph level representation for the network yt. So once we have specified the model, now we are ready to specify the change points in terms of the prior parameter. So let ck, a subset of the time point, be a collection of change points such that the mu, the prior parameter that are in between two consecutive change points, are all equals, while the mu, the prior parameter that before and after a change point, are different. So our goal is that we want to recover the change point from the observed time series of network, where the number of change point k is also unknown. So we're going to achieve this by learning the prior parameters mu1 to mu capital T. So let's visualize an examples for the change point in terms of the prior parameter. So here we're looking at the the mu's in one dimension for illustrative purpose. So suppose we have 3 change points and then they're located at time 26, 51, and 76. So here we are looking at the mu in one dimension. So as you can see that the mu that are in between two particular change point, they are all equals. But the mu's that is after before and after a change point are going to be different. And here we are also plotting the sequential differences. So as you can see that for the differences that are in between two change points, they're all equal to 0. And only when the differences at the change point, you will see a spike or a jump at those change point. So this is our demonstration for the change point in one dimension. But in our case, we are working on the prior parameter in d dimensions. So now we are ready to work on the change point detection problems in this framework. So essentially, we formulate the change point detection problem as a group field/solve problem. So let's denote the log likelihood of the model for y1 to yt as L with parameter phi, which is the neural network or the graph decoder parameter phi and the prior parameter mu. So we want to solve the following optimization problem. We want to minimize the negative log likelihood for the model, for the data, while penalizing the sequential difference between two particular change between consecutive time point. And also the lambda is a tuning parameter for the penalty term. And also the mu t, which is a d-dimension vector, is the t row of the matrix mu, which is a t by d matrix here. So at the high level, we want to use the group fuse lasso penalty to learn the prior of the graph representation so that they can facilitate change point detection. So next, let's look into the group fuse lasso penalty here. So the group fuse lasso penalty, expressed as the sum of the L2 norms, encourages sparsities of the parameter difference, while enforcing multiple components in this parameter difference to change at the same time t. So the latter is called the grouping effects, which cannot be achieved by the sum of the L1 norms. So now let's visualize an example for these grouping effects. So here on both columns, we have the same three profiles that evolve over time. So on the left-hand side, we have the when we use the L1 regularization, we can see that we can learn meaningful change point for the three profiles. However, the change point are not shared across the profiles. On the other hand, on the second column, when we use the sum of the L2 norm, which is the group fuse lasso, we can see that the change point are shared across the profiles. So this is a result or effects that we want in our frameworks. So that's the motivation for why we are choosing the group fuse lasso penalty. So to solve this optimization problem that also involving latent variables, we also need to manipulate the objective function accordingly. So let's first introduce a slack variable nu t that is also a d-dimension vector for time t from 1 to capital T. And then let's rewrite the objective function as a constraint optimization problem. So the only difference is that the group fuse lasso penalty is imposed on the slack variable with an additional constraint. And also the mu t is just the t row of the matrix nu. So when we're looking at this formulation, we can recognize that we can use ADMM to solve this problem. So now let me give a brief introduction about the alternating direction method of multiplier. So the ADMM is an algorithm to solve the following problems, where we have an optimization problem that can break into two parts and also with a linear constraint. So the iterate of the ADMM are defined by the augmented Lagrangian. So we have the original objective function with additional terms, which is the Lagrange multiplier multiplied by the constraint and also an augmentation term. And the updates of the ADMM consist of the following. So let's first fix on the y and the rho and then update x. And once we have the updated x, and then we fix on the x and rho, and then we update y. And lastly, we fix on x and y, and then we update the rho. And then we iteratively implement the three updates until certain convergence criteria are met. So this is a very high-level introduction about the ADMM. And once we have a particular algorithm that can be helpful in solving our problems, and now we can just manually or gradually rewrite our problem into the ADMM framework. So let's first define the augmented Lagrangian for our optimization problem in the following way. So we have the original objective function plus the Lagrange multiplier multiplied by the constraint, and also the augmentation term. And also the kappa is the penalty parameter for the augmentation term. And also for convenience, people usually work with the scaled version. So we also use a scale-do variable w, and we can write the augmented Lagrangian as the following way. And also, in practice, the gradient descent methods may not work well for the group fuse lasso penalty. So we need to further manipulate the objective function for the group fuse lasso penalty. And we are going to do it in the following way. So we introduce two more variables, gamma and beta, where gamma is essentially the nu in the first time point. So it's a row vector. and then beta, which is a t by 1 by d matrix. And for each row of the beta is just the sequential difference of the news. So because we have a time 1 to time capital T's, so they are essentially t minus 1 differences here. So once we use this change of variables, we can rewrite the matrix new, the slack variables, in terms of the following way. So we basically introduce a channel to rewrite the slack variables in terms of gamma beta and vice versa. And this will help us to further ease the optimization procedure. Yeah, so here just rewrite the new in terms of the gamma and beta, and we have the final form of the augmented Lagrangian. And then we can use the ADMM to solve this problem. And here are the 3 updates. So in the first update, we update the neural network parameter phi and the prior parameter mu. And then we update the slack variables in terms of the gamma and beta. And lastly, we update the scale do variables. And then we recursively implement the 3 updates until certain criteria is satisfied. Okay, so next I'm going to talk about or provide some few comments on the details on the updates. So for updating the prior parameters mu, which we essentially have a closed form solution for the updates for a mu t, which is a weighted sum between the conditional expectation of the latent variable zt and the difference of the slack and the scale do variables. So here I just want to point out that the conditional expectation is evaluated at the posterior distribution. And later we will talk about how we can draw samples from this posterior distribution to approximate this expectation here. And also for updating the neural network parameter, the gradients for the neural network parameters can be expressed in the following way. And also we need to evaluate the conditional expectation under the posterior distribution. And next, I'm going to talk about how we are going to draw samples from this posterior distribution to approximate the expectation. And essentially, we are going to use Langevin dynamics to sample from the posterior. The idea is that we are going to implement the following equation to draw samples from the posterior. And the intuition is that we are sampling from the posterior distribution by moving in the direction of the latent variables under the posterior distributions. So we can implement or iterate this particular equation for a short amount of times, and then the z's that we obtain are the samples that are drawn from the posterior distributions. So we're going to use Langevin dynamics to draw samples and then to approximate the expectations for the prior parameter updates and also for the neural network parameter updates. And furthermore, in the second update, to update the slack variables, we also have the closed form solution for the beta and gamma. And when we rewrite the group fused lasso penalties in terms of the beta and gamma, we essentially reduce the problem into a group lasso problems. And then the beta can be updated in the following way. And we can iteratively apply the following equation to update each row for the betas as a block coordinate descent. And then once we update the beta, we also have a closed form solution for updating the gamma. So here I just want to point out that as you can see, the updates for the slack variables do not require the network data, and it primarily rely on the previous update on the prior parameters. Okay, and next I want to talk about the model selection. So essentially, we have a tuning parameter lambda in our optimization objective functions. So we also need to select the model, and we're going to do it with cross-validation to choose the optimal set of change point over different lambda values. So essentially, we're going to break the time series into two parts, into a training set and the testing set. The training set consists of all the network at the odd index time point, and the testing set consists of all the network at even index time point. And then we are going to learn the model with the training set, and then we test, and then we evaluate the learned model on the testing set. And then we're going to choose the lambda that is giving us the maximum log likelihood at the testing set. And then in the end, we will anchor on a particular lambda and to learn the model on the full data again to obtain our optimal set of change point as the final result. One thing we want to point out here is that the log likelihood is also going to be approximated, but this time we just need to draw samples from the marginal, which is the prior distribution, to approximate the log likelihood. Okay, so finally we are going to use two real data to illustrate our proposed framework and to show that generative model can be helpful for change point detection. So we're going to evaluate our proposed framework with the two following data set. So the first one is the MIT phone data, which consists of which consider human interactions via cell phone activities among 96 participants for a duration of 232 days. And the second data set is the Enron email data, which consider email communications before the collapse of a giant energy company among 100 employees for a duration of 100 weeks. So here are the results for our proposed framework. And here we are visualizing on the L2 norm of the sequential difference of the prior parameters. And you can see that most of them are close to zero, and there are a few spikes show up at some particular time point. And then we can also identify some of the potential events that are aligning with our detected change point. And here we are just going to use the spikes that are above our one data-driven threshold that we construct in our work, and then we're going to use those the time point for those spikes that are greater than this red line as our proposed our detected change points. So for the largest spikes, we can see that it's associated with the winter break, which is in fact one of the major events that substantially altered how these students are interacting with each others. And also in the mid October, there's a sponsor meeting where about 2/3 of the students are participating in this sponsor meetings. So we are also able to pick up this particular change point. And then we are also able to pick up some of the holidays and also the spring break with our proposed framework. And the second example is the Enron email data. And then we can see that we have two very large spikes here, which is associated when the CEO resigned and also when the Enron filed for bankruptcy. And then we also have two smaller spikes in here that are associated when the federal exonerated the wrongdoing of Enron and also some confrontations in the public. Yeah, so this is our work for change point detection in dynamic graphs with generative model. So essentially, we learn the priors of the graph level representation to facilitate change point detection in dynamic graphs. And also, our experiments show good performance of the generative model in supporting the change point detection task. In terms of the future works, we also want to develop some generative model that can propose a weighted network, and we can also like develop generative model that produce nodal and dyadic attributes, which are two major components in network type of data. And lastly, we can also develop more complex neural network architecture to facilitate, to capture more intricate of the relational phenomena. Yeah, so I would like to thank my supervisor and also two of my mentors for extensive discussion on graph inference and generative model. And that should conclude our work. And thank you very much.